Welcome to this final panel of the third day of summer school. I am Ursula Costantini, Economic Affairs Officer at UNCTAD Globalization and Development Strategies Division. And this is the fifth lecture of the summer school titled Climate Change and Economic Models. What do they tell us? What can they tell us? As a distinguished speaker, we have Professor Michael Grubb, who's a professor of energy and climate change at the University College London Institute for Sustainable Resources. He has done a lot of work on energy markets and on climate change and sustainable solution for our economies. So thank you very much for being here. As a discussant, I'm pleased to introduce you to my colleague here at UNCTAD, Rodrigo Cárcamo, who is chief of section of the commodities section here in UNCTAD, and has a long experience working in commodities market within this multilateral framework of UNCTAD and the UN in general. So thank you very much, Rodrigo, as well for being here. Without further ado, I leave the room to Michael to start his presentation, please.
Great. So I hope you can all hear me and welcome also online. Climate change has become quite a big issue. I've been working on it for a while. And I decided that what I would concentrate on was the way that economics of the issue has developed. I called it the transition in the economics of climate change and energy transition, deliberate double take, and I will also talk about the role of economic modeling within that for, I think I could say, for both good and bad, and the way that has also evolved. It's now a big topic, if this will respond. Okay. I'll cover first the broad picture on climate change, touch very briefly on the science, risks, costs, the ways that we think about it. I then want to spend a little bit of time on some of the distributional complexities and how that relates to some of the standard economic prescriptions. But I know there's a roundtable tomorrow afternoon as well. I'm not going to dwell much on that. I do want to say a fair amount about technology, innovation, transitions. And since talking and listening about climate change these days can be very depressing, I thought I would add something about there are some positive sides, even if that's not perhaps very visible at present. Some of what I say will draw upon quite a major book that was published a while ago, and with luck will be updated eventually as a second edition with CUP. Okay, so let me start with some of the basic points around what is happening and expected to happen on climate change and the way that this has been perceived and presented through the IPCC. I hope everybody listening at least knows the acronym. It's the Intergovernmental Panel on Climate Change. It's a massive global assessment effort that rolls around once every 5 or 6 years. I was quite heavily involved in the mitigation report this time around. What the science report did was laid out scenarios of, on the left here, global surface temperature change, which shows clearly how the temperature has been rising up to present. The global average surface temperature, for those wanting more detail, the temperature around the poles rises more than the middle, temperature on land rises more than the seas, but it's all going up. A surprising, to some people, degree of potential leverage over what the rest of this century might look like in that diagram on the left. This diagram contains both good and bad news. The good news is actually, I think there is no way that we will see the extremes of those temperature changes on the charts on the left. It was already controversial in IPCC. It would require us to go back to fossil fuels, back to coal, big time, in ways that we just don't see happening. So we're probably not going to see the kind of 4-degree temperature change this year, this century. The bad news on the right is that as the science has developed and the observations have developed, it's increasingly clear that we see more impacts at lower temperatures than scientists had at least hoped for or feared. The way this has been presented, and that's a geeky diagram, because inevitably the global systems are complicated, you can't put exact numbers and thresholds on these, is in terms of 5 reasons for concern. That's the 5 bars on the right. So it's unique risks to unique and threatened ecosystems, the risks associated with extreme weather events, risk associated with broad distributional impacts globally, so the impacts on developing countries, more vulnerable countries, the global average economic and welfare impacts, the 4th one, and the 5th one is what keep the scientists awake at night if entire sort of major global system collapses or fundamentally changes. Collapse of the Amazon, West Atlantic ice sheet, disappearance of the monsoon cycles. Scientists turn up more of those. And so the bad news is we get into the yellow and then red danger zones actually at significantly lower temperatures than was projected in previous assessments. And I'm going to say a little more about this aspect of the risk framework and also how that relates to economics. To do so, I'm going to draw on the mitigation report of the IPCC that was published last year. You can see the scale of the endeavor. Just for clarity, the full report is around 3,000 words. Very few people I know read the whole thing. What political systems really interested in is the fact that the policymaker's summary is negotiated line by line globally under the auspices of World Meteorological and UNEP. So governments have a big stake in it. One of the things that we run through in the report is there are various different ways even of thinking about a problem of this scale. So on the left, I've put some, if you like, broad characterizations. Climate change, close to 20 years ago, was described by Lord Nicholas Stern as the biggest market failure in history. That's the sort of economics framing. It's also been called the perfect moral storm by the philosopher Steve Gardner because of the way it involves fundamental ethical judgments about how much are we responsible or willing to be concerned about impacts on other countries, other generations, how do we take history into account, future emitters, etc., etc. It's also been called a super wicked problem in the social science sense. It's really complicated. Anyone who thinks this is simple to solve doesn't understand the problem. And I'll say a little bit about that. And more recently, psychologists have got in on the act and said, well, Homo sapiens never evolved to deal with something on this scale. How do human beings think about something which is global, where all of our actions affect it, affects future generations, future centuries, even, and the planet itself? So in the IPCC, one thing we suggest is that there are just really very different analytic frameworks. Economics speaks mostly to aggregate efficiency. Obviously, a lot of attention, including obviously UNCTAD, and many of the countries are more looking at national concerns around ethics, equity, who's responsible, who should do what to whom. One area I focused for reasons that will become clear is on the sort of the complexity, but a positive side of it, which is actually our economic systems and technologies also evolve along with all this. And I'm afraid I won't have time to get much into the psychology and politics, but the longer you work in this space, you realize you cannot ignore them as well. But I said I'd say a bit about economics approaches, the framing in terms of an aggregate welfare impact and response. And a really simple level, and a lot of, even today, what economists are taught in their classes about the economics of climate change tends to be framed in this very straightforward way. On the left, you've got a chart of how emissions and some kind of business as usual will grow over time because fossil fuels are great, they power economies, economic development, etc. And then you need to cut emissions because of climate change. You've got various trajectories, paths you can do. And on the right-hand side, the idea is those lower emission trajectories will in turn generate the economic benefit of avoided climate damages. So classic cost-benefit framing, that is basically as structured by one of the famous areas of contribution, Bill Nordhaus, who developed a sort of multi-period equilibrium model to capture all this and re-optimize the system. That has proved, notwithstanding his Nobel Prize, highly controversial. In the standard way that that was run, it suggests a rather odd kind of outcome, which is emissions should dip a bit and then kind of hover around present levels for 50 years, and then you get deep reductions. Why? Because by that time, climate change is getting really immediate and damaging, and you hope that a lot of cheaper technologies have come along. One thing to say is implicit in this kind of structuring is an assumption that the world gets 3, 4, 5 times richer, and who's going to notice 1 or 2% of impact anyway on that time scale. That is not a framing that goes down very well with the scientists or many of the most vulnerable countries. It doesn't go down very well with energy economists either, who look at the sheer time scale of energy systems, infrastructure, etc. And it's been appropriately very controversial because it does embody certain equity assumptions, namely that capital and so forth are totally malleable, and you can argue about welfare, equity weighting. It depends crucially on assumed discount rates for long-term damages. And what about all of the other complexities around impacts, instabilities, risk aversion, et cetera, et cetera. They can completely change the game. One thing that I find useful, if you want to get into this slightly strange world to many people of trying to cost impacts, is this thing called a risk matrix, which says, well, what actually those stylized models tend to generate is identifiable trend impacts on things we can measure, like the cost of coastal protection, need for more air conditioning, stuff like that. They may try and factor in a bit of non-market where you use environmental economics to estimate. Then you might think about, on the left-hand side, climate variability, more extremes and storms, but then what does that do to the non-market? And then you get into those other areas of the way the scientists frame it around those risk charts I showed you, which is, yeah, but what actually about impacts on vulnerable communities? And if you get into systems change of the entire planetary system, and you look at what that may do to the stability of societies that may already well be stressed, and you end up looking at the bottom right-hand corner, which no model captures. How can a model capture, you know, fundamental disruption to the Earth systems and to societies with risks of regional collapse, mass migration, war, etc. So where this kind of leaves the economics is you can kind of feed any assumption you like into these models and come up with radically different conclusions about the outcomes. And I've just drawn, there's a very famous economist, Marty Weitzman, who said, the most important thing about climate change damages is precisely the things that we can't measure. By definition, because the time we have the empirical evidence about extreme impacts, it will be too late to stop them. So actually economics can't help very much. And it was called his dismal theorem about the economics. And there's also some very interesting stuff around an old saying, I think, in the Iraq War. You have known knowns, you have known unknowns. One interesting class is actually known unknown or unknown knowns, things that actually the scientists know, but the political system doesn't want to know about climate change. It's very interesting if you unpick that idea. But broadly, the international effort, at least in terms of UN, has sought to be guided by the scientific degree of concern, rising concern, which the fundamental science is, well, the first thing to understand is this is a cumulative stock problem. It's the amount of CO2 in the atmosphere accumulated over long periods that drives the temperature. You want to stabilize the planet system, you need to get to zero emissions. It's as simple as that. Slight complications, but basically it's true. Therefore, if we want to stabilize the atmosphere, we either have to get to net zero approximately by roughly 2050, if you want to stay in the region of 1.5 degrees warming, or you've got maybe another couple of decades if you want to go up to 2 degrees, but not higher. Under the Paris Agreement, that range was the one that was adopted with carefully crafted language about well below 2 degrees and pursue efforts towards 1.5. There's that risk diagram again. And what that implies is if you want to stay Paris compliant, then you can just do the maths on how much more carbon we can emit. And it's not very much. We're currently emitting about 40 billion tons of CO2 a year. And we have less than 25 years. We can continue emitting that much before we've blown those thresholds. What does that imply in terms of trajectories? Well, this is the IPCC's most recent assessment of that, which starts by saying, well, countries have done some things which might roughly hold global emissions at their present level, slightly rising. The Paris Agreement set up a framework of nationally agreed contributions, nationally determined contributions, which basically, if they're implemented by 2030, yeah, you're slightly down on that, but you then have to drop sharply. The more cost-effective scenarios would be either the green, which probably can stay below 2 degrees, or the blue, which you would need to stay below 1 point or close to 1.5 degrees, with still actually a degree of slight overshoot, gets close to about 1.6 and then down. And as I said, that doesn't sound very scary, right? Only 1.5, 2 degrees. Actually, as I said, we are already seeing very substantial impacts emerging at about 1 degree change, and those are expected to grow non-linearly. So, and that, you know, the more you go, the more you risk these sort of tipping points of some of the wider systems. So this is an issue of, you know, global concern. And I then want to turn to, so what actually would it imply to seriously try and do more to avoid the problem? And for the sake of this talk, I'm going to sort of rule out, oh, we can wait another decade and some technological magical solution will emerge. I've been hearing that for at least 25 years, and I just don't believe it. It's not that kind of problem. Let me start with a little bit about the way, the way that economists then try and frame this in economic terms is, well, what then is the appropriate estimate of the cost of carbon emissions, i.e. the damage imposed by a ton of carbon emissions? There's been a long-running debate in economics. Given all of the uncertainties I've mentioned, of course, it's uncertain, controversial, but nevertheless, it's quite a useful indicator in its way, and the number has changed a lot. Despite all of the economic debates, clearly every time scientists and economists have tried to get together and thrash out some indication, the number gets bigger. The most recent and most serious efforts have been a paper that came out in Nature that was a major effort responding to the criticisms of the US National Academy of Sciences about the way that it had been all constructed before. And what that team, very cross-disciplinary team, came out with was a central estimate. The damage of a ton of CO2 emissions is probably something over $150 a ton. That's 3 to 4 times bigger than the kind of numbers they'd been talking about only a few years ago, and that the US Democratic administration had been saying. And that is, I mean, that's a big issue. You can't quite see the bottom, but it's basically, if that's come through, it would probably more than double the cost of coal if you factored that in seriously, and it would add close to $50 a barrel to oil. Just think about the economic implications of that. And that's basically an uncosted damage, a plausible estimate of. Well, it's worth keeping that in mind. I mean, nobody has the right number, okay? Some people say it's impossible to get the right number, but we know damn well it's not zero, and it's a lot higher perhaps than many people had thought. But the world's a very unequal place. Who should do what in the light of both those constraints and those estimates? So here on the left, you've got what the trend of emission has been. 1990, global emissions were still broadly dominated by the industrialized world. That has changed radically, particularly with the rise of emissions in East Asia. These are the IPCC sort of technically agreed, politically agreed categorization at a 10 region level. But of course, it's not just the present or the last few years that matter. History, it's clear the industrialized nations still dominate historical emissions. That's the graph on the right. The blue is CO2 from energy. The orange is CO2 is net land use. And obviously, there's then a big debate over ideas of historical responsibility versus the sort of economics which, well, it's current emissions that are going to change things. That's where it matters. And others saying, and it's the growth in the developing world that's going to dominate future emissions. So immense scope for distributional arguments. The other way that we cut it in the IPCC is the graph on the right here, which is a distribution across those regions vertically per capita emissions and horizontally the population. It's a great chart if you sit and ponder it, actually, because you can then, the size of the blocks is also proportional to emissions. Again, one thing you see is East Asia now per capita is on a very similar level to Europe, for example. Latin America also, except its structure is totally different because a lot of it is land use. And Africa, a lot of it is land use and non-fossil fuel CO2. So, you know, already it's starting to get complicated, and I've barely started on the, so who could do what and how. Variations are also large in the developed world. If you want to get into more depth, you can also look at the numbers in that specifically. And also, all of that data is who's emitting on their territory. And there's another whole debate about consumption footprints. The rich world tends to import more. Those emissions occur in other countries. Who's responsible? How should that be accounted, etc. You'll be glad to know I don't have time to get into all of that. There'll be another whole lecture, which a colleague of mine is working in that area. One other chart, and I know you have a panel tomorrow on distribution, but I think this is another interesting way of cutting the same data in a way, which is vertically here again, we've plotted countries, this time 20 region, per capita. Horizontally is Human Development Index. And this is kind of interesting. It shows that, yes, a basic level of industrial development has always involved more CO2 emissions. That's intrinsic. You want to build roads, buildings, that takes carbon. As countries get better, the relationship gets weaker and weaker. And you actually see countries all over the place at similar levels of development and even per capita GDP with wildly differing emissions. So you see North America basically in the top right, plus Australia. Everybody needs to get into that into that bottom right quadrant if we are to have any hope of tackling climate change. But the way and the pathway that countries need to take to get there would be radically different. And that's assuming all countries want to maintain or increase their human development. It's a relative index, which is why it doesn't, countries can't go further to the right, right? The IPCC basically from that influenced and indicated that development pathways, all stages of economic development influence greenhouse gas emissions, so they shape the mitigation challenges, opportunities. Development choices are important. They are structurally important choices that countries make. But obviously, the poorer countries with lower human development have got other priorities, sustainable development more broadly, the SDGs, poverty eradication, etc. So there's a very big issue about how well aligned or not is climate mitigation with the other priorities of those countries. I'm sure that will come up in the plans tomorrow, in the discussion tomorrow. I wanted to add one other take on this question, because if you wind back for a second to this chart, the way many economists would interpret it is to say, okay, so the solution is we need to have global carbon price at something like $150 or more. And I think that is a fundamental mistake. I mean, yes, carbon pricing will help. The economic impacts of a carbon price will vary a lot according to stage of development. The degree of responsibility will vary. The assurability to implement and enforce an effective carbon price will vary. It's not something any country can do overnight. And it's actually an incomplete economic solution. And I just wanted to say a quick word about why, which is the economic framing is very much traditionally based around, well, let us assume we have a rational market economy, rationally optimizing agents. Everybody's trying to maximize their welfare, financial optimization. It's a very stylized way of representing human behavior and policy making based on neoclassical and market economics. We actually have seen a lot of the rise of what you might call satisficing, habituation, behavioral economics, which says, well, actually, reality is not like that. Human beings are complicated. Societies are complicated. There are lots of barriers to doing things efficiently and better. They're all over the place. In economics jargon, there are lots of opportunities to get closer to the technology frontier. You know, I've actually yet to see any perfectly optimizing individual or country. It's kind of not what we're like. So it's not uncommon to find opportunities. We're getting people to focus on energy and emissions and say, oh, well, actually, I could be a lot more efficient here. Oh, there's much better technology being developed we're not using. We should use them better. At the other end of this equation or this framing, we are also talking not just about more efficient behavior, but the transformation of massive sectors. Just look at the energy sector. It's probably one of the most complex systems humanity's ever devised. And it just doesn't respond to a carbon price. It responds to all kinds of strategic decisions, infrastructure, capital stock, loads of other things affected by judgments, institutions, etc. And that's the terrain more of evolutionary and institutional economics. And in the book that we run through is, it's not that one of those is right and the others are wrong. It's they all have a role to play for a problem on this scale, from short-term decisions to century-long choices. Social scales from going 8 on 10 billion individuals through to complex transformation of whole sectors. And I think, though people may correct me, quite a lot of developmental economics is struggling across what in the book we call all three of those domains. And this is a challenge that really requires us to understand all three of those. They have very different policy implications. That implies you need multiple policies. Pricing is only part of the equation. You need to think about the sequence of those policies as well. In that third domain, as we call it, that brings us on to, so what about technology innovation and transitions? Here we start to at least see some more signs of hope that I'll build on in the final section if I have time. It is stunning what has actually happened in low carbon technologies over the last decade. So I'm getting a bit more techie for a little bit, right? Left-hand side, solar. The blue is what's happened to the cost since 2000. The bottom is what's happened to the volume deployed. A huge, huge revolution in the costs of getting electricity from the sun. Complete collapse of all the assumptions built into models, actually only 10 years ago, let alone 20 years ago. And the deployment has been growing at something like 40% a year. Human beings, actually, even smarter ones, are not very good at thinking exponentially, but just take a spreadsheet after this, plug in 40% a year, look what happens even by 2030. It's quite impressive. Wind energy, not so dramatic, longer term, but the consequence has also been that in the right conditions, both solar and wind are now cheaper than fossil fuels. Let me just underline that. In the right conditions, both solar and wind are cheaper than generating electricity from fossil fuels. And the cost of batteries have been coming down dramatically on a life cycle basis, again, in the right circumstances. The lifetime costs of electric vehicles are now cheaper than a standard combustion engine. That's a pretty radical transformation from framing the whole thing as what are the costs of mitigation and who should bear the burden. It suggests, wait a minute, this is a much more dynamic and complex process. But of course, it's not simple. but it is transforming the debate and is starting to transform the electricity sector. And I think it's reasonable to talk about the clean electricity revolution this decade. And if you want more evidence, I pulled data from just a couple of months ago from the IEAs, now having to do 6 monthly updates because things are changing so fast. And investment is increasingly dominated by renewables investment. Not sufficient, we can come on to that, but still setting the global records. Well, how did this happen? Because we really should know and think about the implications. I'm part of an international consortium that's been looking at this, that's tried to bring to bear some of the new, both economic theories around evolutionary of economic systems, economics, complex systems, and modeling, dynamic systems modeling. But we started by saying, let's start with the evidence. I don't have time to go into detail. We looked at 3 case studies: wind, efficient lighting, each of these with respect to countries we were working with. So Brazil has been a really important player in the emergence of global wind energy at scale, the first big developing country, in fact, preceding the explosion of Chinese wind. And that was important in the global development. Efficient lighting, India got involved. India did procurement on a mass scale that ultimately has led to the most efficient lighting actually also delivering the cheapest lighting in history, as they called it. That is a phrase that you may have heard as also being used for solar as now the cheapest electricity in history, and that is the International Energy Agency. Common characteristics, well, I've put the words there, but if I can maybe just stress that. All of these were led by strong government action, but all are now largely self-sustaining. They would not have been pursued under traditional economic cost-benefit framing, nor were they driven by, let's just have a massive carbon price to make this stuff viable. No, the common themes were cumulative progress, building upon previous R&D and technological and industrial development, but not really blue skies lab breakthrough. Market-based innovation, market-led often, but driven by policies that created scale. Through sustained and targeted support beyond R&D for usually a couple of decades. Of course, there were a lot of uncertainties at the beginning of these journeys. Germany actually probably spent £100 billion on its energy vendor that drove the markets for some of these. That's not a trivial contribution to the global effort, but strong international dimensions. Yes, the industrialized world could take this process a certain distance, largely of itself, but the big cost reductions really came from also the expansion of supply chains and production to China and to other centers with lower costs. And of course, that itself was controversial. Where does this lead us? Well, let's do a mind flip away from what's the marginal cost of this stuff to what are the dynamics of the systems we're now in. And they tend to draw in a stylized way something like the right-hand side, which is these things happen through some kind of S-curve process. Stuff takes a long time to develop initially, gets a foothold, looks small, but it's growing exponentially from a very small base. Suddenly you realize that exponential growth really means something big when it continues. And it starts to challenge the incumbent industries. It then usually hits political and institutional walls because the markets don't suit the new types of technologies. But by then it's starting to also face political resistance because it is undermining the market of the established technologies. And ultimately, you probably have to have fairly major institutional and market structure changes that suits the new characteristics. Yeah, I mean, a solar panel is not just a new way of doing a big coal power station. It's really not. It's fundamentally different. And overall, energy and industrial systems are very path dependent. I won't run through all the slides on this, but it's partly induced innovation. The more you do, the cheaper stuff gets, therefore the more you do. That's one well-known thing that drives path dependence. Infrastructure is another, but a whole series of things mean that actually energy systems evolve in various directions and can then be pretty hard to change. In policy terms, in the IPCC, and based also on that sort of 3 domains framing, we mapped out a simplified, stylized way, but you need 3 pillars of policy. Typically, these transformations are being led by strategic investment, a significant degree of government subsidy, But then you have to get serious about the market structures, the structures of pricing in those markets for the stuff really to lift off, to give industries confidence that these will not always be dependent upon government subsidies, there'll be real markets. And they may then start to require changes or views of norms, behavior. People need to believe and trust solar panels on their roof and that they can sell power back, and electric vehicles and that they charge, et cetera, et cetera. So you've got this kind of evolution of the policy mix to really drive these transformations at scale. Okay, I'm going to move the final part of this, and sorry, I've covered a fair amount of ground, but just a little more about signs of hope and opportunities that emerge. This is another chart from IPCC and a research paper underpinning it that took a while to get acceptance because there's been so much drilled into us that everything's getting worse everywhere on emissions. And it's like, guys, it's actually no longer true. We have made some progress. There are 24 countries that have sustained emission reductions. Most of them had legally binding targets under the Kyoto Protocol. That led to a whole series of implementation policies. But however you measure it, some countries have started making progress, predominantly industrialized, that started from higher per capita, but that has gone along with a lot of learning, a lot of technology, etc. So if I now turn in this context to what do economic models tell us, there's a kind of fairly cynical answer, which is, well, economic models will tell us whatever the modeler or the funder wants the model to tell you. To some extent, that's true. But it's the scientists who said the original economic casting is totally inadequate for the risks faced by climate change. And now more and more economists are saying those models are also totally inadequate for a world of systemic innovation, path-dependent systems, co-benefits of mitigation, etc. So the more sophisticated variant is that traditional economic models have a deeply embedded theoretical framing that tends to draw us towards an assumption there's some kind of aggregate optimum equilibrium out there and the global carbon pricing is what you need to solve it, which immediately pews up massive equity issues. Or you can think about, can the right sophisticated policies that foster innovation help to get us out of this mess? We need to broaden the toolkit. Accept that to some degree economic models will tell us what we tell them to tell us, but that actually we have learned a lot more interesting questions that we would like models to inform us about. They include risks, intergenerational equity, distributional dimensions, fundamentally changing our framing of the scale and seriousness of the climate problem, which is going to disrupt 21st century development everywhere unless we get it under control. That it must also include the dynamics of energy and climate systems with a rapidly growing sense of urgency, but includes policy and technology innovation that highlight opportunities in tackling the problem. So without going to delve into the detail, you have to get a bit sector specific. There are 6 major sectors at stake here. The IPCC assessment is there are options now in all 6 of those sectors that can be materially pursued over this decade to start getting us on the right course. You can delve into all of the sectoral chapters that run through that. I am fortunately wrapping up. So just to drill home my point, critique, but also opportunities around modeling. The default assumption of the dice-like models is what I call temporal independence. There's a magic equilibrium out there, we just predict it, and there's not much relationship and dynamics are not that important. We have to have models which have more dynamic realism, complex systems, lots of inertia, lots of induced innovation, lots of path dependence. We need models which give us better handles on those kind of systems, because that's the reality of what they're dealing with. But this is not a Panglossian view of, it's okay, folks, we've actually got the solutions now, because it hinges on policy and finance. And I'm afraid I couldn't resist dropping in a slide from an article that I had published in the Financial Times only last Friday, which says we have a difficult, long-standing, painful standoff about climate finance. But we actually, if we are smart, we have the opportunities to break the back of that. And one of the potential key players would be Norway. Why? Because Norway over the last 2 years has made 150 billion pounds of windfall profits from its energy exports. That's a lot of money. 150 million, $1,000 million sitting in the Norwegian oil fund, and they don't know what to do with it. But they're smart, and hopefully they will work out that if they particularly underwrite international investment risks in clean technology, that could get us a very long way. And my final slide is the following. It's a conceptual slide, but it's one I think now that has a lot of empirical foundation, and on which I found a 3,000-year-old saying, which says, no wind favors those who just don't know where they're going. In other words, we do actually need a sense of governmental agency over where we need to be going in a climate-constrained world, and what that says about the policy environment domestically and internationally that has some chance of getting us there, recognizing this is not a marginal cost added on a fossil fuel-based system. It is a radically different kind of energy system appropriate for the 21st century. The transition is already underway, so far mostly driven by not the pure market prescriptions. We need the different pillars of policies that I touched on to be a mutually reinforcing package. It's not that you can do one and forget about pricing. They're all important. It does imply a degree of industrial and development strategy to shift development pathways. It does imply a degree of social engagement, political license to do these things, and clear policy direction, which above all needs to start not magically producing, trillions of totally public funded money, but which shifts the investment risk as perceived by the vast pools of private capital that we know are out there, and to persuade countries that there are things to gain from the low carbon transition. So that's and I think that can now be done. We can see how it can be done. And that's my sort of more optimistic end point. Thank you.
Thank you very much. It's quite impressive how you managed to navigate the complexity of all these topics, and it's fascinating how you can tell how hard and for how long you've been working on this topic. It's actually inspiring. And I have to add also that we know quite a few people downtown in Geneva who also earned quite a bit of money recently, and but I wouldn't bet on how smart they are about it, or they can be about it. So let me just, without further ado, give the word to Rodrigo.
Okay, thank you very much. First, I would like to thank the colleagues of GDS for the invitation to us to be here. And the first thing I want to say, it's very challenging after such a great presentation to be able to say something coherent and that might be interesting. It has been really a fascinating and extremely comprehensive presentation, full of data, full of analysis, and full of food for thought. So what I'm going to do is I'm not going to try to do any of that. What I'm going to do is I'm going to focus on some specific issues that were mentioned by Professor Grubb in the context of what we do here at UNCTAD in terms of commodities. So before we start, we start talking about the connection between commodities and climate change, I want to share with you this graph, which is available in a new publication we have just made in June of this year, which shows the countries which are commodity dependent. And you can see the darker the country is, the more commodity dependent it is. And you can see that the distribution is quite easy to detect a pattern, okay? So 101 countries, 95 of which are developing, because there's only 6 developed countries that are commodity dependent, were in the last 3 years for which we have data, export commodity dependent. And this number has pretty much not changed in the last 25 years. We have, UNCTAD has been monitoring this for a long time. We have a dedicated publication called The State of Commodity Dependence that you can find in our website, where we have done that. And there's a paper published in 2019 where we actually looked at the last 25 years, comparing what has changed. And in practice, it's very little for many countries, with a couple of exemptions. And commodity dependence, like you saw in the map, is pervasive in 3 areas, which are Africa, Oceania, and South America. And it, even more importantly, it affects a disproportionate share of countries with special needs. 81% of landlocked developing countries, 74% of LDCs, which is on 3/4, and 61% of small island development states are commodity dependent. So that means that the poorest and most vulnerable countries are then the most exposed to commodity price volatility, which is the topic I'm going to focus on, which is related to our topic, with very little capacity to absorb negative shocks. And here it's another graph, which shows, on the one hand, we previously saw commodity dependence, that is the percentage of commodities are a share of exports. Here you see the export concentration, which is not the same. We use the adjusted taste T index, which is a measure like the Herfindahl-Hirschman index of concentration. And you can see, for example, the countries in South America, even though they're very commodity dependent, they're much less concentrated, because even though they are commodity dependent, they export a wide variety of commodities. However, the countries in Africa, they're very, not only commodity dependent, but also concentrated, because most of them, they export 1 or 2 commodities. We have a table in our publication showing countries who export 75, 80%, 90% of their exports are one product, one. And here is just a graph to show you the difference between commodity-dependent countries as a percentage of developed, small island development states, other developing countries, and LDCs. So we can quickly move over that. Now, what is the connection between climate change and commodity dependence? Well, we have just seen that all these countries are extremely dependent on the export of commodities. But we also know that, as Professor Grubb has very clearly shown, that there's a carbon budget that is not very big, that needs to be met at one stage if we want to achieve the target of 1.5 degrees increase or 2 degrees increase. So that will inevitably mean that a large percentage of the commodities exported by these countries will be affected, either via changes in land use, like he mentioned, or countries who export energy. So one issue is that there's a large risk that the assets exported by these countries will become stranded. Stranded assets are those assets, for example, coal deposits or oil deposits, that will not be able to be fully exploited and exported if we want to meet those targets. And that's especially true for those deposits that are particularly polluting, like the case of coal. So, second important challenge is that, as Professor Grubb mentioned, that there's a significant amount of risk and uncertainty that affects the models of climate change and also growth models. So when we try to measure not only if we're going to meet climate change targets, but how that affects growth, the models that are in use are very poor at incorporating this risk. For example, fat tails in the distributions. If you replace simply a normal distribution for another distribution with fat tails, you get a completely different result. Or even worse, what happens when you have the probability of low probability events, but with very large negative shocks. For example, we're seeing now that El Niño is combining with climate change to create quite a bit of havoc. and in ways that is very difficult to predict. And we are only at the beginning of the transition. What effect would a large El Niño effect have in 10 to 15 years' time when we are still have not peaked into the mission of, and what effect will have that on the production and export of commodities? Second point. Third, commodities, present a persistent cyclical behavior in real prices, which is combined with non-stationarity. That means that you cannot identify a trend that you can extract from the series. The series are mostly non-stationary. There's quite a bit of work on this. There's a very interesting review paper in the Review of Economic Statistics published a number of years ago when they analyzed a lot of series, a lot of products across different times. And what they find, and a lot of other studies have found, is that the prices move up and down and in unpredictable ways. And also an important thing, which is important for the risk issues that I was mentioning, is that these series are co-integrated. That means that there's a common trend across different commodities, even different commodity groups. So it's not just that the price of soybeans is correlated as expected with the price of sunflower, because both produce oil, but the price of oil is correlated with the price of corn, for example, through these regulations like use of maize to produce ethanol. There's a lot of work that has been done across that, but that's another issue. All these issues and several others interact with access to finance. Like Professor Grubb was mentioning at the end of his presentation, access to finance is a key point, especially in the context that we have, as we was discussed yesterday by Professor Jodorowsky and Anastasia, heterogeneous financial market developments with cycles, with large and sometimes not fully accounted risks, with very large shadow banking systems, which present risk in different countries. And also we have incomplete and imperfect capital markets that was also discussed. Many developing countries have pretty much no access to loans in domestic currency, so their capacity to face these issues, for example, self-insure in the face of a negative commodity price shock, is very limited. We can talk a lot about that. This combines with large, lumpy, and often risky investments into adaptation. The report, the IPCC report, I have not read the 3,000 words, the 3,000 pages, but I have read the technical summaries, I admit that, and they go quite a bit in depth into this. And in terms of risk, for example, let's take one technology, carbon capture and storage, that has been touted by some people as the silver bullet that's going to solve everything. How risky is that? For example, we look at one project, the Gorgon project in Australia, what was expected ex ante and what actually happened was quite different, just to give an example. So this is quite risky and costly, and you have to put the investments which are sunk at the beginning. So add to all the points that we're mentioning. So all this affects the capacity of commodity-dependent developing countries to successfully engage in a structural transformation with value addition on the basis of their natural resources. Now, I'm going to go a little bit more into the commodity price volatility, which is something that the commodities branch at UNCTAD will look quite a bit. So as I said, prices are follow persistent, multi-year cycles. They're positively correlated. Volatility is also heteroscedastic. That means that volatility is not stable over time, but actually grows or reduces, and it clusters around events. For example, Professor Jodorowsky yesterday showed the aggregate price of the Bloomberg price cycle, and you can see very clearly these clusters of volatility. And it's also heterogeneous across products group. I'm going to show this now. For example, while agricultural commodity prices are on average less volatile than energy or minerals, the volatility within the group is very large. We're discussing this with Amis a couple of weeks ago. So here you have just one series, the agricultural deflated prices deflated by the US CPI for the period 1994 to 2023. You can very clearly see the cycle. That is a trend extracted with standard Christian Fitzgerald filter, bandpass filter. And you can see in black the real agricultural price index. You can see the volatility along the trend, very, very large. And it's also clustered around events, for example, the international financial crisis. Here you have in this box plot, you can see the prices in blue for 2017, 2019, and in red for 2020, 2022, the summary distribution. And you can see that the prices of agriculture on the left-hand side are substantially less volatile than minerals, energy, and in the case for the last period, fertilizer because of the war in Ukraine. So there is very large, very significant differences, statistically significant across groups and even within group. I'm not going to show the one within group, but that is also available. So here, what we did is, in this, we just used two different measures, very simple measures of volatility. On the vertical axis, the coefficient of variation, and on the horizontal axis, a robust measure, which is the quantile coefficient of dispersion, which is equivalent to the mean and the median. And you can see on the left-hand side, the volatility in the 2017-2019 pre-COVID period, and what we had in 2020-2022. And you see on the upper, you may not be able to see on the screen, but on the right-hand side, you see that the energy prices and fertilizer prices had massive volatility increases, but also agricultural prices divided by subgroup also did. So what are the implications of this volatility for these developing countries who are now vulnerable to significant weather events and climate change? What does it mean for growth? What does it mean for poverty reduction? What does it mean for development? Yesterday, Professor Giorozzi was, and my colleague Giovanni the other day, were talking about capital inflows. And there's a very large correlation between commodity prices and capital inflows, as he mentioned, especially for countries who are more integrated into international financial markets. There's a very large correlation between commodity prices and GDP growth. There's a very large correlation between commodity prices and fiscal revenue and net foreign assets. We have differential volatility also across the value chain for certain agricultural products. Why is that important? When we're looking at commodity prices, people usually tend to assume that we have one single representative agent producing and exporting this stuff. But in practice, we have a smallholder producer with half a hectare in the middle of the jungle, in the middle of nowhere, without roads, selling to an intermediary who sells to another intermediary, who sells to a larger intermediary, who sells to an aggregator, who sells to an exporter, who may receive a fraction minus the cost of transport of the international prices that you saw. So what happens inside that value chain is also extremely important. That's something that UNCTAD has been looking at. We have done some work on it. So that's why I only mentioned it, but we don't have time to discuss it. So that suggests that the micro impact of volatility may be higher for these smallholders and others. So policies are necessary at all levels to address this issue. Now, just to show you some things, this is how the commodity cycles are correlated with capital inflows. I took the cases of two countries that are financially integrated. One is Chile, the period 2005 to 2021. You can see that, and below you have that the test is a statistical significance test that shows that it's strongly statistically significant, the correlation. And there are other tests, I only included one, and the same for Brazil in the period 2005 and 2021. This is for capital inflows. Now, what is the direction of causality? I think we can discuss, but as commodity prices are mostly exogenous for most countries, probably the direction of causality goes from there. Second, this is a commodity price cycles matter for growth. We have now on these graphs, how the growth of the different countries. We have the same, Chile and Brazil for the period 1976 to 21 and 1961 to 2021. You can see the trend and also a very simple test below of the linear relation. Two more slides. One more slide. Thank you. Okay, so thank you very much.